In the last video, we took essentially the length of y equals x squared, not the length, but we went from 0 to 1 on the x-axis, and you can kind of view it as this area. And we rotated it around the y-axis to get this figure here, and we figured out the volume, and I think our answer, if I remember, was like pi over 2. And we used what I called, and what everyone calls, the shell method. I want to show you that you could actually use the disk method here, but then we'll just have to switch the y's and x. Instead of writing this, write the function as a function of x, we'll just take the inverse of it and write it as a function of y. So this curve, y equals x squared, what it can also be written as, we could just take the square root of both sides as x is equal to the square root of y, right? Just take the square root of both sides. And now we can use this information to do the disk method, but everywhere where we had an x in the past, we'll now have a y. So let's think about how we would do it. So it's, once again, it's this area. So, and this will take, and then really the hardest thing about all of these problems is just the visualization. And I think that's why they do it, just to make sure that you know how to visualize things and maybe understand the calculus. It's more visualization than calculus, really. So we're still dealing with, if we take a cross section, if we were to just cut this figure, it would deal with this area would be the cross section, right? So, and we're still rotating around the y-axis, just like we did in the last video. We're still rotating around the y-axis, we get this figure. So how would we deal with disks? Well, a disk would look like this. Say at some point, let me pick another color. So at some point, we'd have a disk like that. That would be the top of the disk, and then it would have some depth, right, like we did before. And its height, or the radius of that disk, would be equal to x, right? It's equal to x, and I know you're thinking it looks like the shell method, but what is x equal to? It's equal to the square root of y. It equals the square root of y. And what would be the width of that disk? Well, now we're making everything as a function of y. So the width would be just a very small distance, dy, the differential y. And of course, all right, and so that's essentially all we need to know. So the volume of that disk would be the radius squared times pi times dy. So hopefully that makes a little bit of sense. But there's another hitch on this problem. This is actually similar to what we did 2 videos ago, because when you view it in the y-axis, from this y, you could kind of say frame of reference, what we're going to do is we're going to take the volume. We can take the volume of x is equal to 1. Right? So what would be the volume of x is equal to 1 rotated around the x-axis? It would be just the entire cylinder, right? So we're going to take, it's really important that you visualize this right, what we're doing. So we're going to figure out this volume. The volume of x is equal to 1. Let me draw the axes just so you know what we're doing. So this would be the y-axis. That would be the x-axis, as best as I could draw. And so what we could do is, originally, we can figure out the volume of the entire cylinder, right? This is x is equal to 1. X is equal to 1. From what y points? From the point, well, what is this? This is y equals 1. This is, y equals 1 to 0. So we would figure out this volume from y equals 1 to 0. And how would we do that? What would be the integral? And remember, everything is in y now, so it might seem a little confusing. And so what is, for each of these disks, right? This is going to be made up of a bunch of disks. Let me draw one of them. So let me draw the top one. The top disk, and it has a width, and it's not going to be this entire cylinder. Its width is dy. Its width is just going to be this. dy, very small sliver, dy. And its radius is x, or you could say f of y, right? So what would be the volume of that disk? Well, it would be the surface area of the top. So it would be f of y squared. Remember, we're dealing everything with y. F of y squared times pi, that gives the area of the top. Put the pi outside of the integral. Times dy. dy, and we said y is going from 0 to 1. y is going from 0 to 1. So that's that entire cylinder. And what we'll want to do is subtract out, essentially cut out the volume of the inner bowl. So minus. And so how would we figure out the inner bowl? Well, that's where we will deal with the x is equal to the square root of y function, right? Because here, what's each disk? Once again, it's f of y. So I wrote this generally. This is f of y of the outside. And I'm going to now do it for the inside. I'm going to cut out the inside volume. And since I kept it general, I could do it. We're still going from 0 to 1, from y equals 0 to y equals 1. These, remember, we're dealing with y now. And now we'll take f of the inside, f of y squared d of y, right? And you can imagine, in this case, the inside function, we're going to take the volume, and here, that original disk I drew is actually one of the disks for the inside function, where the height of that disk is dy. That should be dy. The radius of the disk is f of y, and of course, the area of the top of the disk is pi times the radius squared. Now, how do we apply it to this particular situation? Well, what is the outside function? F of y, x is equal to f of y. We're just switching the variables. And we said that x is equal to 1. This is just a big cylinder, right? So f of y is equal to 1 in this function, so we get pi, let me switch colors, times from 0 to 1, 1 squared dy minus pi, and we're still going from 0 to 1. And remember, that's the y boundaries. And now what's f of y? Well, here f of y is square root of y. Square root of y squared dy, right? And so this equals, let's take the pi out. So this equals, I'll write it up here. So pi times, well, 1 squared is 1. What's the antiderivative of 1? What function's derivative is 1? Well, it's x, right? X, that's the antiderivative there. And we can kind of merge these. We took the pi out. This y, square root of y squared, this is just y, right? Oh, sorry, no, the antiderivative of 1. See, even I get quite confused here. We're taking this with respect to y, right? So the antiderivative of 1 now is y, right? We're summing up a bunch of y's, right? I'm sorry. I find this even a little perplexing when I start switching x and y's. But then, let's take the second function. Remember, we can merge these because it's the same boundaries and they're both with respect to y. Square root of y squared is y. What's the antiderivative of y, the function y, or y dy? What's y squared over 2 minus y squared over 2, right? And we're going to evaluate that at 1 and 0. And so what does that get us? So we get pi. So we get 1 minus 1 half. 1 minus 1 half. Minus 0 minus 0. Minus 0 plus 0 over 2. Whatever, these are 0. 1 minus 1 half, that's 1 half. 1 half. And then times pi is equal to pi over 2, which is the exact same result. And I was worried because, you never know when you might make a careless mistake, as I often do. But we got the exact same result as I got in the previous video when we used the shell method. And so the hardest thing here is just remembering that you're doing everything in terms of y. And instead of the disks, when we did the disk method traditionally, the disks were vertical disks. Now they're horizontal disks, but it's the exact same thing. And you just have to get your brain around the idea that we're dealing with the y's, that the boundaries on the integrals are now y values. We're taking the width of the disks are now, or the height of the disks are dy, and the radius is now the function of y. Hopefully, I didn't confuse you too much. I made, my own brain malfunctioned a bit when I took the antiderivative of 1 dy. It should have been y. But I will see you in the next video where we will do even more complicated problems where I'm sure I'll make even more mistakes. See you soon.